All right, Anas, thank you for coming. Would you like to introduce yourself?
Sure. My name is Anasthas. I graduated from Syracuse University, and I have a master's degree in geotechnical engineering. And right after graduation, I joined a local firm called CME Associates, and I've been working with CME Associates since. So it's over 13 years, and I'm a senior geotechnical engineer and do a lot of soil investigations and foundation designs.
Okay. And could you give us a brief overview of the project here and how CME was involved in this?
Sure. Today for this project, we're going to talk about a project, a local project in Cortlandville. It's a burn dairy cheese factory building that was planned to be built about 2 years ago, and it's actually already built. And before they started the planning process, they hired CMA Associates to go in and do some soil borings, do some investigation type work to plan for the foundations and for the building design. So I'm going to show you where the project is located and some specific about the project on the maps here I have. Okay, so as I said, the project is in Cortlandville. So if you go down Route 13 through Cortlandville, as soon as you pass the Walmart, and then there is a miniature golf course, you go past that, that's where the site is. It's a huge site, and the existing grade is not flat, it's low around this corner, and the grade is higher back in this corner. So the idea was to build a new facility about in this location here where the grade is low. But there's one problem with this site is that if you know anything about Cortland, you get a lot of flash flood. And as a matter of fact, about a couple of years ago or 3 years ago, the new Walmart that was built on Route 13 flooded actually. I have some pictures. Let's see. You can see this is back here. You see the Walmart building. They're trying to save these people from the building. And you see inside the store the flood all over the place. So significant flooding that occurred right after the store was newly opened. So as you can imagine, building a facility like this needs a lot of planning, especially for the flood condition. So the fact that site being lower in elevation, the design team decided to build up the site by about 5 to 7 feet above existing grade and then put the building. So the idea was to see if they can use some of the on-site material to fill this area here. This area being high and this area being low, the initial thought was to see if we can do a cut and fill balance at the site. So they decided to select this area as their borrow pit, and this area is the building. So I'm going to show you some details on the project. Let me try to zoom out a little bit so we can see the whole picture here. I think that's the maximum zoom out. Okay, so we have to move the pictures around here. So anyways, so here is Route 13 on this side, and here is that low area I talked about, and this area here is slightly higher in elevation, probably 3 to 7 feet higher than grades here. So the thought was to cut some material from this future expansion area and fill the lower area here to build this facility. So this building is the proposed facility that's about 60,000 square feet building, pretty good size building. If you go into a Lowe's or a Home Depot type building, the square foot area of that building will be about 100,000 square feet. So this is about 3/3 of the size of a big Lowe's building. 60,000 square feet building. And so the initial stages, the owner hired us to do some subsurface exploration consisting of soil borings and test bits to give foundation recommendations. So that's how we got involved in the project, and we got carried through all the way through construction and inspection.
Okay. How do you determine what tests for subsurface exploration have to be carried out?
Good. So a site like this, what we have is a lot of earthwork here, because if you think about this site, you're going to raise this site by about 5 to 7 feet of structural fill to get up to your finished floor elevation of the building. So that's 7 feet times, say, average density of 135 PSF. That's over 1,000 pounds per square foot load that you're putting on that site. So in addition to the weight of the building, you had to consider the weight of the fill material that you are placing. So that's a key factor here. So you need to know if there is soils that are susceptible for consolidation, soils that are susceptible for compression, shear failure, and things of that nature. So soil borings are needed, and the soil borings will give you an indication of how dense the material is and what type of material we have. Say if you have clay materials, you can actually bring clay samples and test in the lab. So we definitely needed test borings, and we also needed test pits because this is a cut and fill site. So we need to see bulk samples. We need to test bulk samples to see if those soils can be used on site to build this building pad. So therefore we used test borings and test pits and infiltration test on this job.
Okay. And could you describe what sort of laboratory tests were carried out subsequent to these borings and test pits?
Yes, well, yes, we performed, when we did the test pits, we took bulk samples. Like I said, the owner was planning to use some of the on-site soil for fill in his building pad. So we took bulk samples. The primary tests, a majority of the tests were compaction tests, laboratory compaction tests. That's the Proctor compaction, you will call. And we did some natural moisture content tests. We did some sieve analysis, and in the field we did infiltration tests.
Okay. And how do you determine the number of laboratory tests that you're going to do? Is that influenced by, say, the building code, or does it depend on other factors?
Well, the subsurface exploration in the field work, the building code actually gives the engineer who is designing the project, for in this case, the foundation design will be a geotechnical engineer.
Okay.
So the building code allows us to use our discretion as to how many test borings that are needed for this project and what type of test that should be done. So, for example, in this project, as a rule of thumb, you will need at least 3 borings for a building and 1 boring for every 5,000 square feet area.
Okay.
Okay, so in this case, I'm not sure how many borings we used, I can't remember, but we used our experience of local projects, and we already knew what soils to expect here because we have done some work in the in the vicinity. So we substituted some of the test borings with test pits, and majority of them were test pits, and some of them were test borings.
Okay. And could you describe some of the limiting factors to conducting the laboratory tests, whether it's financial or something else?
Yes. So in the initial stage, this is before the building project is bid out. So we are doing our exploration work and lab work, right?
Right.
So you cannot spend a whole lot of money on things that we are not sure if that's going to be needed in the future. So initially you select the minimum number of explorations and lab tests that are going to be required to do the design accurately. And then during construction, you see if the conditions assumed were similar or different. If it's different, you go for more testing. For example, in this case, from a compaction test standpoint, one thing I forgot to mention is that this project is a major earthwork project because there is tremendous amount of fill. It's over 100,000 cubic yards of fill material was used to build this building pad. That's a lot of material. So compaction is the key test on this job.
Right.
The laboratory compaction and the field compaction. And the laboratory compaction is very important because that's what's going to tell you what the maximum density of the material that you are using to fill this site, and that's what's going to tell you what the optimum moisture content is. So when you do a laboratory compaction test, you are going to plot that curve that's going to look like a parabola, and the apex of the parabola is your maximum dry density, and the corresponding moisture is the optimum moisture content. You need to know those two numbers to be able to do the quality control in the field. So what you do in the lab is very important. So the lab testing, compaction testing, is the key test on this job.
Okay.
So when we did the exploration, we took bulk samples. We took about 5 different bulk samples, and we ran compaction test in the lab. In our lab, we have a lab in CME, and we plotted those curves. Those curves were later used during construction to do the quality control on the fill material that was placed.
Okay. And from the borrow pit, what did those Proctor compaction tests yield for results?
Well, the borrow pit that the owner was planning to use as fill material for his site, we had soils that were not so good for structural fill inside building pad. We had clayey soils, clay and silt soils. The problem with clay and silt soils is that they typically tend to come out of the ground in a moisture content that is higher than the optimum moisture content that you will find on your moisture density relationship curves.
Okay.
So what that tells is that that soil is too wet, and if it's too wet, it's near impossible to compact it to bring it to that maximum dry density. So the contractor will have a very difficult time compacting that to achieve the quality of material that's needed for the building pad. Number 2, if it rains, it becomes wet, you cannot compact that material at all. Whereas if it's a granular type material, you will be able to compact relatively easy. In this site, we had clay type soils and also gravel type soils. So we were able to use both of their soils outside the building, not inside the building. For the inside building, we had to import some granular fill.
So you were just talking about the labs. I was wondering if you can give us an example of how that data was used for the compaction in the field and what materials were placed.
Sure, exactly. I'm going to show you some pictures to show you the type of material that was used in this job. What you see here in this picture is a imported granular fill material which was used inside the building footprints. Here you're going to see some on-site sand and gravel material mixed with cobbles and oversized particles, and here you see on-site fill material mixed with some construction debris, and here's another type of soil that was used. It's mostly silt and clay type materials. So there was a number of different materials that were used on this job. Now we can come back to and so for each different material that was used in the job, we sent samples to the lab to test for Proctor compaction. So the lab sends us the Proctor compaction results. So you know the maximum dry density and the optimum moisture content for a particular material. Say for example, the silt and clay.
Mm-hmm.
So you know the maximum density and the optimum moisture content for that material.
Mm-hmm.
You take that number and you plug that into this machine. This is a nuclear density gauge. This is the most common test method that's used in the industry for quality control of structural fill.
Okay.
So what you do is you input the maximum dry density of the material that you are going to test, and you take this machine, you push this probe into that soil, and you press this button, and it measures the in place dry density of that material.
Okay.
So you have to make sure that you are inputting the correct maximum dry density for the material that you are testing. Because like I said, there were like 4 or 5 different material that was used in this
Mm-hmm.
job site. So the technician who goes out in the field needs to know how to classify the soils and compare that soils with the lab data to see, okay, which proctor I should use for this material. So he takes that number, puts in here, and press this button, and it's going to measure the dry density of that material, and the machine will automatically calculate the percent compaction.
Okay.
Basically, it's the dry density of in situ soil divided by the maximum dry density that you got from your lab compaction test times 100. That's the percent compaction. So the specification of the project will say, okay, the fill needs to be compacted to 90% or 95% depending on where you are testing.
Mm-hmm.
So if it's 95% and if your number comes out to be 96, passing density test.
Okay.
The technician is happy, the contractor is happy, move on to the next lift. They put another lift, they test it, pass, that's how it goes. But the important thing is the technician needs to use the right proctor because there are different materials on the site. So that's how the quality control is done in the field.
Okay. So with that in mind, how influential would it be if some of the lab data you received was incorrect, or the tests were done incorrectly, and how would that influence what's going on in the field?
Good question. Most of the times, if the lab test is flawed or the data is incorrect, there is a procedure called submittal review process. So you do the test in the lab, you send the material data to the contractor, and the contractor submits the material data to the project architect, and the project architect reviews the data to make sure that the results seems okay or satisfactory. So if there is any issues with the lab test data, for example, if it's silt and clay soils and the maximum dry density comes out to be like 145 PCF, then something is wrong, because silt and clay cannot be that dense. It should be in the range of like 120 to 130 or even less.
Mm-hmm.
Or if you have really well graded sand and gravel type material and the proctor compaction results comes out to be the maximum density is 120, then someone will question this is too low for that material, so they will have them retest. So even if you bypass that procedure, and if you come to the field and if you're testing and all of a sudden your densities are coming up on the machine 102% compaction, 105% compaction, 120% compaction, that cannot be right in theory. In theory, you cannot compact something more than 100%. So that will tell you something is wrong with that proctor.
Mm-hmm.
Or sometimes the contractor will use the right material, right moisture content, right equipment to compact. He will be passing several passes with the roller and will still not achieving compaction. You are getting 70%, 80%. It's way below the required compaction.
Mm-hmm.
So that tells the proctor value that we are inputting in this machine could be wrong. So at that point, you have to recheck and retest.
Okay. All right. Well, I want to thank you for coming here today. We're very excited to be using this project as a case study to do work on calculating cuts and fills and compaction, doing cross sections of the soils. And I just want to ask you if there's any last bit of advice you want to give these students before they embark on this project.
Thank you. It's really my pleasure to be a part of this class. And my advice would be to get your hands dirty in the lab. Because some of you may never touch soils, but if you are in the geotechnical engineering field, you need to have hands-on experience. Your technique is not something that you can study in the book and be proficient at. You need to play with dirt, so put your hands in the dirt and play and learn.
All right, thank you.
You're welcome.